Analysis and Design. Before we begin, let me introduce to you our subject interest group. We call ourselves ESIC, the Education Subject Interest Group. If you log into the new website of the IChemE, you can find us over there in the community page. You can also see the URL loaded on the slide. This group is meant to exchange information between universities and industrial practices. We tend to develop a network of interest committed to education mainly, okay, and the what we call the current practice in the industry, and whatever we want to train our students to be. So this is a platform where we can share our expertise and the ideas for best practices in chemical engineering education. We promote continuous education activities and the profession in school as well. Right. Our ESIC consists of probably about, let's say, 10 to 15 committees. Currently, our chair is Gregor from Herowatz University. Our vice chair is Yaka from Newcastle upon Tyne. Secretary is Andrew Hotley at Monash University. I myself, I forgot to introduce myself. I'm Dominic Fu from University of Nottingham, Malaysia. I'm the chapter lead at Malaysia. We have our treasurer, Alice, and webmaster, Thomas. Today we have our webinar. I should also introduce some upcoming activities. We have the ChemEng Day UK to be held at Herowatz University in Edinburgh in April, 9th of April. And that is the education's sort of symposium. Besides, we'll have another webinar scheduled somewhere around May or June. Please get updates from our website later. We'll have a process safety teaching seminar, a face-to-face seminar scheduled in August later to be taken place in Kuala Lumpur, Malaysia. Right. Let's move on. Let me introduce to you our speaker today. Dr. Zulfan Adiputra is our speaker today. He is the Senior Lecturer of Chemical Engineering at the University of Technology Petronas. This university is based in Malaysia. His interest of research and teaching is on system engineering, process synthesis and development, process optimization and integration, as well as process safety. Prior joining to academic, Dr. Zulfan worked at several institutions. These are multinational chemical companies in R&D and process engineering division. He is nowadays an active consultant for industrial companies, both in Malaysia and Indonesia, where he's from. And today he's going to talk to us the early phase process synthesis and design, looking at the stage gate approach for process evaluation and selection. Before we begin, let me also remind you that this webinar will be recorded. If you are an ESIC member, you are welcome to log into the portal to listen to the webinar again in a couple of days. And by the way, nowadays all the IChemE members are free to choose as many as you like the subject interest group to join. So please welcome to join our education SIG as well. And towards the end, we'll have a session for question and answer. However, you may leave your question in the question portal on the to-go meeting, wherever you like to, because at the end of the webinar, I will read out the questions for the speaker to answer. All right, without further ado, let's begin the webinar today. Zulfan, mic is for you.
Yeah, thank you. Just checking, I'm loud and clear, right?
Yes.
Okay. Thank you very much, Dominic, for the introduction. And this is my first time having a webinar for myself. So let's see how we go. The topic that I'm going to bring today for all of us is the one that I think it's worth sharing. So I took this from my previous experience on how when we do early phase evaluation on different technologies or on different process routes or in different catalytic systems, we all follow the same. I mean, I would say the same pattern or the same method. So in that sense, I think it's worth sharing. In this early phase process synthesis and design, I will highlight about the stage gate approach that we do during this evaluation and selection. So we will share this with you. The things to discuss during this webinars, we will talk a little bit more what are then the relevant industrial research problems, and then how do we then approach this systematically, how we can find some solutions in it, yeah, and then how we can then at the beginning we generate ideas, and then what are the tools that we can use, and then how we design such process. And then do we know how much cost would that be? How much then profit that we might be able to gain? Can we have some insights on the technical part of the process or some economical part of the process, which we normally call this like techno-economic analysis, which I will just share with you as well. And then lastly is then how sure are we with the solutions that we got? Because as we know from the title that it is about early phase process evaluations where there are high uncertainties present, and we're not really sure. But then in that to tackle that issue, I mean, how can we at least have some level of confidence to say that yes, indeed, this is then the right way to do or to go. Some of these industrial research problems are like maybe now we're having like competing raw material prices with now we can purchase one materials from different suppliers, and then they both have different specifications in some sense, and they have both different prices. And then if you were asked by our managers to say, okay, now tell me which raw material then that we should buy, and then with that question in mind, we should then be able to say, okay, if we use this material, yeah, maybe we will need to tweak something in our process, or maybe if we use the other material, we might need to not do anything, or we might be able to do something more. It could also be that the current process that we are running is not really competitive enough because it's too old. It's old technology, for example, or it's just like because the way that we are operating it is not like safe anymore, or it's not like consuming too much of energy. It could also be that when we do the operations, the R&D people, our colleagues, they have found new product, and then they ask us, "Can you make something out of this?" So as a chemical engineer, then we are obliged to be able to answer that questions. There are also like questions on. We are too much dependent on a certain supplier. Can we try to have like a raw material securities? Can we find more suppliers that can, so that we can have like competing schemes between our suppliers, so that we can have I don't know, like more flexible in that sense? Or maybe to make the same process or to make the same products, there are new informations that we can have like a safer route, or like a more economical route, or more environmentally friendly route. So, but then the question is again, which one then are we then going to select? It could also be that the current market that we are now producing, the current chemical, is already a saturated market. So in that sense, if we are going to make to produce the same product, can we use this in a different way, right? Or can we make more produce downstream products? So these are also kind of questions. It could also be like we have the increasing cost of utilities. Probably new raw materials are found, so this is then related to the competing raw material prices as well. And then could also be like increasing cost of waste treatment, which is also related to the utilities. So many things like dependent or like linked to each other. And then these questions lead us to ask ourselves that can we do something about these situations? As you can see, there some of these questions, they are links to each other, and some of these they are and some have some correlations. But basically, if I see it in general, we have like at least like two big items to think about. it is then the raw material securities and also the product diversities. At least these two are very common to be found in this type of research questions. From these questions, we know that we are going to have like a very complicated and very uncertain situations. So that needs to be tackled in a systematic way. And as we know that once we get the answer from this question, that doesn't mean that we can then start away build the plant or start away then make the product and then sell it. There are some procedures or protocols, or what we call this like gates. In some companies call it gates. So there are some certain stages that we have to follow so that from the idea we can then transfer this into like a marketable product. So that takes quite some steps. In the chemical project life cycles, normally we have this stage gate approach. So we are starting from the idea generations, answering the questions that we have on the previous slides, and then out of these generations on how to solve them, we might be able to find, I don't know, maybe like 10, 20, 50, or even 100 solutions. If we do like a brainstorming, there's many techniques of doing this brainstorming. And then out of this 100, we're not going to apply them all, but we have to be able to select them. And then maybe in this evaluation step, we will do some evaluations, and then which we will then select out of this 100, for example, we can come up with maybe 10, 20 selected ideas. And this is 10, 20 selected ideas. We will do some more selections, evaluations, do more in-depth study, and we do some feasibility study in that sense, which in the end, at this point, at this gate, we might end up with maybe one or two routes or technology or process. And then at least one or two, we then work together with contractors, or if the company that you now are working with has like a strong R&D or strong some support in the engineering, they might be able to do some basic engineering design for that selected route. And then after this stage, we go to the next stage with this gate. We work together with the engineering contractor to do what we call something called engineering, procurement, construction and commissioning, and also start up at this phase. And then once the plant is up and running, we do the plant operations, we do also optimization, we do also debottlenecking, also answering the questions on the previous slides. And then the whole cycles begin in answering those questions. We start from ideas, feasibility study, basic engineering, and then so on and so forth until we think that we are, this plant is good to be demolished or not. So the way it works is from this left to the right. And what I'm going to share with you today is about this phase. How we then, from these idea generations, how we can come up with some tangible solutions, and then how sure are we, how we can have some level of confidence in it. This is then this webinar is all about. In the idea generations and feasibility stage, in this case, we normally have like idea generations on to tackle one of these problems, and then we do some like process synthesis, like flow chart or whatnot. And then after that, we do some process design. So these stages is also like how do you call it? Out of that big stage of idea generations and evaluations, we have like this sub stage, so to say, and then where we can have some small gate in between. In the idea generation phase, we do normally like a literature review. We see what other people have been doing. Can we then adapt that technology to ourselves? Can we then tweak it a little bit just to meet our need? We could also do some brainstorming to see what other ideas from different perspectives from the other colleagues that we can then combine or adjust to solve our problems. And we might be able to do some experiments as well. Or if we have done some experiments from our colleague in the chemistry or in the in the chemistry department, we might be able to use their results as well. And then from this data, and then we can make our own input-output diagram. For example, we're going to make like a chemical B from chemical A, and we should have some data like yield or conversion or selectivity, some rough number that we can start with. And then when we do then the input and output diagram, we know that, okay, so this chemical A makes chemical B. Is there any like a byproduct? Is there any like other utilities that we're going to need, for example, if we know it? And from that on, we then try to put some numbers. And then I would like to call this like input-output mass balance. So we have like incoming, we have like outgoing, that the one that the product that we're going to have, and then based on the information that we have, like a yield, selectivity, conversions, or whatnot, then we can make like a rough mass balance from this input and output diagram. And please remember that all incoming streams, they have to have like their output stream. So we cannot just say like for making A to B, we have like chemical C, and we don't know what to do with the C. So there's something that we have to be aware of. Yeah. While doing this, for sure, we will have some missing informations. Is this the correct yield? I mean, is this then also the correct catalytic system that we can use? I mean, is this then the properties that our customer wants? Some questionable results. We could also see, like, if the temperature increases from the experimental or from the patterns or from the literature, some doubtful and weak points, which we can also make a list out of this, and then with this information, input and output mass balance, if we then can gather some indicative prices, I would then say that we could make like we could calculate something they call economic potential zero. So we have the input streams with their prices, if we know them as much as possible, and then we have the output streams and also their prices as much as possible, and then we can calculate our economic potential zero. So from this, like say 100 or maybe 50, I don't know, routes or possible solutions, we can then quickly screen them by using this approach into like some few selected, something that we can bring on to the next stage of the process, which then the process synthesis in this case. So this selected view, we try to dig deeper. Right, so we do some more experiments if we have to, and then we do some more literature review specifically in that selected process, and then we do some more brainstorming. And then when we develop the process, we try to develop the process not only we base our process based on the input and output diagram and mass balance, and we dig deeper, which I will show you in the next slides. To make the process more more readable. And in that sense, we have to think in functions. So this block diagram is to do a reaction, and then after the reactions, roughly this is then the phase of the reactor outlet, and then what to do then. So we can then have like a quick max balance to say, okay, this product B is the one that we want, and I don't want to have like A and C. So we have to have like another block diagram to say I want to have them separate. But at this point in time, it's also sometimes it's easy to say, yeah, okay, we can separate them by phase only, or we just have to create the phase by increasing the temperature, for example, or reducing the temperature, and then after we create the phase, and then we can just easily separate them. If we can do that, that's also better. If we can't, and then there's something to be to point out and to list down. Why can't we do it at this point in time? Is it like do we miss any properties? Or these are like not so common chemicals. And once we finish with this block diagram, we start making some mass balance. Yeah, it's just we start from here, and then we just make it more detailed based on the block diagram. And then from this mass balance and the block diagram, we could roughly, I would say, do some capex estimates. There are many approaches to do this, which we can find in textbooks. Like we can find, for example, we can find like a similar process, number one, and then we can just tweak it into our capacity. Or we could also find, like, if we can dig deeper into this block diagram, this is a kind of distillation column, for example, and this is a bit difficult to separate. So we might have some sense, especially if we in this team we have like a senior engineer working with us, so he or she has some feeling on how difficult or easy the separation this separation would be, or this reactor, is it like a do we need like a fancy reactor, so to say. And based on the experience, we can have some estimates on the capex. But still, I think from this discussion so far, we are still missing some information, right? Is this the right reactor? Is this then the right place to add these two reactants? Is the we have like the right mixing? So all of these questions, and then we have to also list them down. But in this new block diagram, which is more detailed than our input and output mass balance, in this new block diagram, we could say then, okay, now I have little bit more detail on the mass balance, so I know then how much then the stream going out as waste or as byproduct, or I might need some this utility like steam or hot oil or even refrigerations if you want. And then based on these capex estimates, I would say then we could do something called like economic potential 1. So this economic potential 0. So we add capex to it, and then we can then get the economic potential 1. And the result should always like be positive. So if any of these few processes that we are now evaluating, if any of them like they have like a low value of economic potential, we can just discard them, or even negative, we can just remove them away. So from here to here, we already, I think we can then reduce the options to few and few and few, and then from these results, if you move on to the next stage, we can do then the more analysis. We can search more in the literature. We can do some more experiments, and then I'm having a feedback from somewhere. So then in that sense, we could also have some advice on what type of reactor can we use. This is just for example, yeah. And then can we now have like a more detail on what kind of separation unit that we're going to use? Is it absorber? Is it distillation column? Is it membrane? Or is it just like a sedimentation? Can we have some recycle, or do we need to have some recycles? These things we can answer in this phase. And then from this block diagram, if we dig deeper into putting these new informations, we can make our process flow diagram roughly. Yeah? It's not like the process flow diagram in full detail, but it's just like a flow diagram that we have more detail compared to the block diagram. And from this flow diagram, we might be able then to calculate not only the mass balance, but also the energy balance in this case, because we have specified the type of separation reactors, the heating and the cooling that we require. Based on this, we can also do then a better capex estimate with the accuracy of -30% to until 50%. Still then, at this point, we still have some missing information, questionable results, and doubtful and weak points. But at least the list that we have here will be more specific, more and more specific compared to the list that we have here, and also compared to the list that we have here, which is normal, it has to be the case. And by including the energy in it, the utilities, we can then subtract the economic potential to economic potential 2, I would call it. So that means the margin from the product that we are selling, minus the raw materials in here, minus the capex over here, and then minus the utilities over here. So we have less and less and less margin. So with this, I think pretty much we can then reduce these ideas into only a few, maybe 1, 2, or 3 maximum. This whole work, if we do some economic potentials, that means we have some economic information in it. When we list down all of these questions, for sure, these are then like technical list of questions that we have to bring forward. So this whole technical list of questions in our line of work is that if we want to move forward, that means we have to be able to answer these questions or that questions, so that we have like a strong how do you call it, a strong justification on how to move forward. So we have unknowns, and then we list down these unknowns. So to be able to select this process over the other, or to be able to say yes, we are going forward, these unknowns, we have to be able to answer them. So it's very critical for us here to know what we know and to know what we don't know. Uh, um, 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 so if we don't know, or if we are in doubt, then we can just list them down. I'll show you some examples that we did. So right from here, from the idea generations, I will then move in this sense, yeah, in this manner. So the ideas, for example, yeah, I'll just take one example for my previous work. So we have like a raw materials over here, and then we have like products over here. These are then the things that we know. So the question at the time was that using the same raw materials, can we diversify the products? So we have like this products and that products, and if you have more products, you can also do that. But then the question is then how to produce this product. So I'm now copying the work from Al-Hawaii. So they call it like forward and backward process synthesis. So if we know that we have this raw materials, so what can we do? So if we have this process, we can make that product, and then from this product we can make many other products. Yeah, so we have 1, 2, 3, and so on and so forth. Many processes, we can make these products, and from these products we could also make another products, this product and that product, and then from this process, this product, for example, it can make, yeah, it's more like, if you can see that this is more like a backbone of backbone chemicals, with which we can make many products. And if we move from here to there, we see what products can we make from these raw materials. If we move along to the right, we are moving forward in this process synthesis. What we could also do is then we are moving backward from from this tree. So this product, for example, what kind of raw materials can we have to make them? So for example, to make this, we can have 1, 2, 3, and 4 raw materials with these 4 processes. And then from this product, is there any raw materials that we can use to make this product? So yes, indeed, we have this products to make this, and that product is then processed via this process from this product, and so on and so forth, until we can have like a connections from forward and then backward. So if these connections, you can see there are so many connections here from here to there, so many connections that you can make. So this could then symbolizes the amount of routes or processes that we can work with. But then it's quite a lot, and I don't think we need to we have enough resources to go deep into one of them. So we start from that first stage. So we do like input and output diagram, as we discussed before. So if you can see, like, this is step 1, step 2, step 3, and so on, step 6. This symbolizes that the process in itself. So this is then process 1, and then from here to there it's process 2, from here to there it's process 3, and so on and so forth. So in each of this process, we have some information on the yield, some information on the consumption, and we try to put as much as possible. And then on this input and output diagram and mass balance, if we don't know that information, it's fine. Just put all of this the things that we know. We need to have like a raw material, for example, some tons per hour, or raw material, another raw material, some B. If we know it, if we don't know it, just leave it blank. But at least we have to put them. They have to be visible, so that later on, these unknowns, we can then do further investigations in the next stage to answer how much this unknown is. The same goes with the waste, and then the product, and then this product is then going to the next step to make another product. So we do another mass balance around here, and so on, another mass balance around here and there and here, and then step 6. So if we know that we can have some recycle somewhere, just put it there. So try to make this input and output diagram as much as possible, of course with the limited time and resources that we have, but that's fine. And then from here, we can then like sort of closing the mass balance, yeah, even though we don't know detail, but at least we know, if we know some of these numbers, it's more like a puzzle. So if we know this, and then we know this, and we know that, and then we don't know some of this, but we know this, and then we know that. So some of these we might know, the others we don't know, but then try to see if we can then find as if we can then close this mass balance as much as possible. And by having this information, that's not too much of information, it's just only like a yield or conversions or collections or whatnot. And then we can then have a list of these many 10 or 20 processes, yeah, depending on the how many steps, yeah. And then we can then quickly calculate the economic potential zero, and then make a make them in descending order. So the top the process that are on the top list would then be the preferred ones, and then on the bottom list would then be the ones that we're going to discard. And then we can calculate the economic potential zero. So from this one, we move on to the next stage. We have like a block diagram. So in this case, for example, we dig deeper into step one. What do we need actually? So in this step one, we have one raw materials, and then the other raw materials, and then these raw materials, they have to be mixed and then put a reactor and then make a we have like a liquid and gas situation as we know it, and then we try to separate that gas gets back recycled and then goes to off gas. This one, it could either just a splitter, it could also be like another separation point which we will need to note it down. And then we go to the next column, next operation unit, and then the other operation unit, and then the other operation unit, until we get our product in this case. And then if we have some heavies, which we can then purge, or we can just strip them and then put it back into the reactor. So these options on having this splitter, purge all of this column is just a matter of like in this case, we don't do like a process simulations in detail yet, so it's just like a feeling. So that's while the feeling, I mean, so our like only based on our knowledge so far to say yes, we have to separate them to get my product, but that doesn't mean that we know how in detail. Do we need to have like a we don't know yet how many stages do we need, for example, for distillation column, or can we then say this liquid and gas separator, is it like a simple flash column, or do we need to work around it somewhere? And the mass balance that we get from the input-output diagram, we try to put it well in more details in here so that we know some recycles, we know some another details on the mass balance. So we can roughly then size if we need to have like cooling, if we need to have like a compressor, for example. How big is this column, so to say? How big is that column? So if this one is then going to be recovered from the top because of the boiling point, for example, and if this one is then going to be recovered from the bottom, and we know that this amount is then huge compared to this amount, and then we will then have some sort of idea that the shape of our distillation column would then be like a ketchup bottle upside down in that sense. So these are then the insights that we could gain so far. And from that block diagram, so we try to go into that process flow diagram, and we try to make it a little bit more detailed. So we have some reactors with some sponges in this case. We don't know yet how it looks like in the end, but just make a simple sketch. We have like a 1 column, 2 columns, and 3 columns with all of these auxiliaries, and then we try to put our input and output. We put some mass balance around it if we know it, and then the question is then now, okay, so this main raw materials, it's coming from a tank, I would say, and then this tank will then come, I don't know, it comes from rail car or from trucks, and then we then have to be able to think about how often this truck is then coming to our plant, and then this another raw material, is it like a utility from the utility grid, or is it something that we have to buy as well, or is it something that we can produce? And this purge, for example, does it go to flare, or is it go to, in this case, to fuel system, or just like chemical waste? And this water, for example, does it go to the wastewater treatment plant or whatnot? So all of these inputs and then the outputs, we should then have a feeling on where they're coming from in regarding to the raw materials, and then where they have to go regarding the outlet streams. So you can see now here these all red things, the things that the one that we don't know. So now, for example, in this reactor, if you look into deeper, I put some numbers, I don't know. It says from the literature review or from our experimental results from the batch reaction that our chemists have done in the lab. So they say they need to have like 120 minutes. Then as a process engineer, we should ask ourselves, do we really need this 120 minutes? Can I see your data on conversion and selectivity in terms of the operating conditions? Right? So these are the questions that we can ask or poke to our chemist colleagues. Let's see if they get angry at that. I don't know. And we could also say we have some catalyst information, for example, and then do we need to prepare the catalyst? We need to like some catalyst recovery system. How much is then the catalyst that we can that we have to put in the system? And then are they like commercial, something that we can just buy, or how expensive that is? So all of this, yeah. And the other questions like this, so what is then the effect of purity to the selectivity? Do we have that information? Do we have the kinetics? Right, which we normally don't have the kinetics. And then do we know all the products? These are then the basically what we always missing as far as I experience. Because the chemist only understands we need to make that main product, and they don't really care, or at least not really aware on the other minor products. But for us, that matters a lot. And then we want to have like a heat exchanger. Do we have enough data on the thermal properties? Do we know the thermal conductivity? Do we know the heat capacity, heat of evaporation, heat of vaporizations? And then when we do them some separations, do we have the vapor liquid equilibrium? How accurate that is? And then is there any solubility data or other properties if we want to do like a compressing and transporting like pumps? And then do we have like a density, viscosity, and so on and so forth? So these are the questions that we can make a list. If yes, then we put the number if we know it. If we don't, and then just make a list of that. And from this, as you can see now, we have more detailed equipments with mass balance around it, so we can have some sort of a feeling on how big the equipment is, which we can then use to calculate our capex and then calculate our economic potential too. So from this exercise, we can then try to remove more and more alternatives. We could also do some cost estimations here. And the capex. So this just I put some in-house cost estimating tool that we have. And then we could also like this cap cost. I don't know if you know it, but I think in the universities, students normally use this. If not, they will be using things like Aspen or not. But at least we need to have like a same basis when we are going to evaluate this, because we know for sure that these numbers are there based on the correlations given by suppliers. But then how accurate that is, it's still a matter of our uncertain situations. So once we get our cost estimations, we put that number back into this same process flow diagrams. So we can say now, so this compressor is about 5% of my total capex, for example, and this reactor is about 20%. This unit is about 12%. This is about negligible. I don't know why, but then this one also is about 31%. So now you can see the significance of each section of this process, which we can then pinpoint. Okay, how do if I want to make this process cheaper, that means I have to do something here and something there, right? This, okay, I can live with that. I can take this risk and that risk. So we don't directly jump to say, okay, I need to have like a new catalytic systems in this case, which you could argue, right? Because if you have a good catalytic system, higher conversion, higher selectivity, and also if you have like higher conversions, that means you don't need so complicated details. But you could also argue, okay, we cannot do anything more in this regard, but in that sense, to make this process more competitive, that means we have to do more here and not there. So with this exercise, we can then focus our next research on what to do, and where to investigate. And then if we know what to do and where to investigate, that means we can then have some feeling on what kind of resources that we can allocate to solve these issues. So if I put them all in summary, this is just example of some general remarks, so technical remarks. So how are all raw materials supplied and outlet streams are handled? And then what is then the effect of purity to selectivities? Do we know all the products or main and byproducts? Operating windows, properties, what kind of utilities? So all of these which are required, like a list of questions that we need to have before we can say, yes, we are going to select this process over the other, or we can say this is then going to be one of these selected views to be able to be evaluated further. And also the economic remarks, as you know, as we discussed before. So we have some insights on whether or not we need to have like a cheaper reactor, different catalytic system might be needed, or a different way of reacting it. Which columns is this then? Is the decision column is the only way to separate that? Can we have a different and cheaper separation unit? This catalyst, can we just purge this, or we have to do some treatment? And if we do some treatments, how good is that treatment so that we don't lose too much of catalyst, for example, and then some waste chemicals? So these are then the questions that we have normally, apart from this NPV, IRR, and then payback period, which we normally see in literature if they want to do like techno-economic analysis. But then the real chunk of the work is then finding this list of questions, because this list of questions is then the backbone or the strong foundation to say whether or not we have to go further with this process. If we have long list of questions for one process, that means this is then we are going to need more effort, a significant effort compared to the others, so that we just better for the time being we keep it in view. I mean, put it in the like a fallback option, so to say, and we move on with the other options that have like questions that we think we can handle for the next stage. Once we know what we want to know, right? This one. And then we can then have like, we make in this case particularly, we did some like a category on raw materials, and then what are then the process development team, for example, is it like this specific case, so we can have like the status of the current situations in this category, and is there any requirement? If not, you can just leave it be. So from this status, the current status in this stage, for example, what are the gaps so that we can then move on to the next phase? Because the next stage, for example, we need to have certain information. This is normally then defined by the company requirements before we can move forward. Or in our case, if you don't have such requirements, we can have like, okay, if I want to make my process better, that means I have to increase some selectivity. So if the current selectivity, for example, I think I have to, if the current selectivity is like 94% at 50% conversions, can we increase this higher to 97%? Because we know that if we know that from the block diagram that we have before, this recycle, for example, that recycle consume is a big recycle, hence we have big equipments in this region. So can we increase the selectivity further? If not, so to increase the selectivity, what are then the resources that we need? Maybe we need to have like some months or some FTE or some amount of money to do some more experiments. And if we have some challenges, then we can just list them down. And then what is then the impact if we cannot achieve this? What is then the impact on the project? or on this particular process. So we do this assessment on various process design categories. We have this raw materials, and we have this selectivity and others. And then we make this list. And then we can then see, okay, so from this counting, I need to have these resources, right? So from this analysis, I need to have these resources, and then this estimate of FTE and time to complete, roughly. Yeah, this is not rocket science. And then from here we can go for feasibility. So so what would then be the next informations that we need? And then in this process synthesis part, okay, we need to know this hydrodynamic, we need to know this, we need to know that. So to know this, roughly how many months, and then roughly how much then finance, and then how much FTE, how long is then we require. And then from here we can do, okay, once we have this, say that we have this, so what are the things that we need to do more, so that we can say, okay, this is then going to be one of the process that we're going to go for the next basic engineering phase, for example. So we need to do more upscaling experiments or pilot plant setup. We don't know. So depending on case-to-case basis. So we do this exercise, all of this exercise, for this 1 or 2 selected processes. Yeah. Now, once we get this 1 or 2 or 3, maybe, I don't know, processes, and then the question is then, how sure are we on these cost numberings, or on all of this? So what we normally do is then the Monte Carlo simulations. We also do like what we typically do in sensitivity analysis is that we fix one variable and then let the other variables vary. And then we plot it in this so-called like a tornado diagram. But we know in practice we cannot fix the other variables. We cannot vary one variable while fixing the other variables. What happens in practice is that all these variables, they are changing randomly. So if we have some important variables, depending on our, when we do this analysis, we know some important variables to our cost values. So these important variables, for example, the price of chemicals, the price of raw materials products, that makes normally the huge contributions. So activities, conversions, and other important variables. We have some default numbers for these, and then we might have some ideas on what is then the minimum and maximum values. They do not necessarily to be like in the middle. Yeah. So if we have like this is then 500, this is then 1,000. This is not necessarily like 750. Is not necessarily so. If we don't know, yes, maybe we want to make like a minus 50% plus 50%. But if we know, if we have more information to say, well, my selectivity is now about 95%, but we know that it's going to be very, very, very difficult to go above 97%. But we often see like 80% selectivity in different conditions. Yeah, so that means it's not like it's skewed more to the right in that sense. So we have minimum value of 80% and then maximum value of 97%, and our default value is about 95%, which happens in practice. So we put them all together, and then in this Monte Carlo simulations, we let them vary, and then we let them the simulation run like 1,000 times, and then we can get this kind of plot. So we have like a frequency, how many times it appears, and then the capex, if we can calculate the capex. So if we have like 2 process routes, say, okay, process route number 1 is the blue one, route number 2 is then the red one. So we can see like, well, majority of this process, capex wise, is just slightly lower than the one here. If we only do like a default number, we might end up one is over here and the other one is over there, and we can see, well, it's quite a big jump, yeah, from 600 to 750, for example. But if we do these variables, we know that these 2 processes, they are overlapping quite huge. So capex wise, we don't know if route 1 is better than the route 2. Let's see if the operating cost. So now in this operating cost, even though that this route 1 seems to be like slightly more cheaper than the route 2, but operating cost, OPEX wise, we know that route 1 from this Monte Carlo simulation, it is then well, the overlapping region is much lower compared to this overlapping region. So in that sense, we could say, well, this area over here is like, I don't know, maybe 80%. So we have like 80% chance of this route 1 becomes more expensive in operating costs compared to route 2. We could say something like that. But then if we combine this capex and opex together, for example, yeah, we do more exercise, and we end up with this kind of stuff, which is now we're back to square one. Yeah, we don't know which one is then we're going to select, but that's fine. At least we take this information into account, and then we make like a 1, 2, or 3, and so on and so forth. So if we have like one raw material to make another product, and then we have 2 routes to compare, or we have another product here and then another route, it's also fine. With the exercise so far, we have now the knowns that we have the unknowns that we have to recognize, and we have seen some uncertainties on this based on this exercise, the Monte Carlo exercise. And then we can then have a feeling on to consider, okay, with this list of questions on when we do the techno-economic analysis, when we do the Monte Carlo simulations, we can then ask ourselves, okay, with this information, which route then? And then yes, I now have some confidence in saying that, for example, we know, well, this total cost will not be lower than 90 and will not be higher than 190, so it will then be somewhere in between. At least we narrow down the certainty or the uncertainty that we are now facing. We can then, with this information as well, we can then say, okay, I will then select this route, for example, because it seems easier to do, or it's we can have this route in the shorter term compared to this one, yeah, based on that process readiness level assessments that we have done. And then if we want to do this, for example, what are then the scenarios that this route might fall down and then we have to take the other route? So these are the questions that we have to sit together and discuss and then bring forward to the management. And then if we don't know, yeah, some of these questions and this techno-economic analysis, we need to, for example, we need to do some more research on a particular aspect. And we look at our research department, if they don't have such capabilities, and then we have to go online, if we go outside of our company to see, is there any other institutes or universities that we can work with, or other research group? Normally, we have like companies providing like service on doing the experimental works. They have like a high throughput experiments, for example, or they have like a specific reactor that we can borrow, right, to see. So these are the things that we have to consider when we say yes, we need to buy, or we can just collaborate to do some tests. So last is that we do normally like visual comparisons. We have seen the techno-economic analysis. We have some numbers in it. From this list of questions, we might be able to say the probability of success or the maturity of the process over the other. And then if we have like a different raw materials, for example, and options to choose from, and we could also say put that. So all of these three, for example, they are in this particular case, we combine them into like a process attractiveness. So these numbers, 40%, 20% makes 100% of the process attractiveness. These are then like our own criteria. Yeah, you can make your own criteria, and then you can also make different names here. And then here we have like does it fit to the company's vision? So if we have like a IP, can we patent? Can we have more technologies? Can we is this process fit with our current competence, or do we have to outsource more? And then can we leverage our company situations at this point in time? So again, this whole is then criteria is their own selections. And we at that time we also put like this HSE safety. This is then the size of the ball. So safety, health, and environment. So you have like one route is then is more dangerous than the other. one is then less safer, one is then emitting more CO2 than the others. So we can have this size of the ball, and then make some this is then going to be like a mix of quantitative and qualitative assessment, and you might end up with this kind of visual. So we have 1, 2, 3, 4 processes, and we can see that this process is then the least attractive. That process is more attractive, but it does not fit well to the company's visions. Yeah. So what we want to have a process that is as close as this area, so it fits to the company's visions, and it is very attractive. But we normally don't have what we want, so we have like a trade-off in some sense. So this process, for example, it fits a lot, the most, to the company's vision. And in terms of attractiveness, it's also not so bad, even though it's not the good one. It's not that bad. And then the size of the ball, the safety, HSE, safety, health, and environment, it's also quite okay. So this is then the very maybe the less safer or less environmental friendly process, if you can see from the size of the ball. So and then you can also play around with these numbers and to see how these balls move around. Yeah, and then in this sense, we can then present this with the elaborate in-depth analysis on each of these, which we have done before, and then present this to our boss or manager or whatnot, to say, okay, this is then these are then my first option, and then this could be then, I don't know, my fallback options. Yeah, because it's entirely on the company's visions. For example, if I take this is more important than that one, but then to get this more effective, we need to do some more extra work. So this process, it must have like a much longer list of questions compared to this process. I think I'm done. So how do we do this again? We start from the brainstorming. We do the process flow diagrams, and then we do like a Monte Carlo simulation for sensitivity analysis, and then in the end we do some selection criteria. I think I'm over my time a little bit. With this, I think I close my presentations. So if you have any comments or questions, just let me know, and then maybe we have some time to discuss. So yeah, thank you.
Thanks, Zulfan. Thank you very much.
Yeah.
There is well, probably we have only a few minutes left. Let me ask you the question that I have here. Andrew from Monash, Andrew Hartley from Monash, Australia, asked this question. I wonder if inherent safety is considered in each of the 3 stages of the approach. Is there a formal process like HAZOP?
In this very early stage, we don't normally have like detailed PNIDs, and hence we don't have HAZOP. But what we do have is some companies that I've seen that they have like 7 stages of hazard studies. So stage number 4 is then the HAZOP. So stage number 1, 2, 3, the hazard study 1, 2, 3. It's more about, for example, 1 is about raw materials. And then we can then see, okay, and in terms of the, we can see from the MSDS or NFPA level. So we can see this raw material is then the more environmentally friendly than the others. And then stage number 2, we can see also like we put more on like a process, operating conditions, and so on and so forth. So these are then the safety studies that we can do at this very early stage, not the HAZOP yet.
I guess HAZOP, you need to get the PNID, process equipment layout. How many? Okay, let me see. There's another question. Thank you so much. I am quite fresh in process design. I get interested. Is there any resource that I can study or do some online course on this sort of project selection?
Yeah, that's a difficult question for myself. I
wonder this book of Warren Cedar.
Yeah. That book is one of the good ones that I would recommend and consider. And then another one that I always use. There are 2 that I've been 3, I think. I don't know. I'm using a book from the this Colson that I think this chemical engineering design.
Volume 6, huh? Chemical Engineering
Yeah,
Volume 6.
volume 6, but they have the latest versions. What's the name again? Synod and Toller, Toller and Synod. Toller and Synod,
Right.
the latest one. It was the Chemical Engineering Volume 6, but then they put some more data on it. And then I use like there's also like integrated design and simulation for chemical processes from Demian and Bildea and Kiss. I use that as well. And also Robin Smith from Chemical Process Design and Integration. It's also good books. So having these 3-4 books at hand, I always have these 3-4 books. Yeah, I have it now in my cupboard. So whenever I find any, I need to find some more information, I always look up in those books, especially in the designs, because we don't remember much of the stuff.
Right. Nuno give us a website or https iniped.com. iniped.com is a good source according to him.
INIPED. PED. Okay, INIPED.com.
Another one is can refer to Harvey Barron.
Harry Barron. Okay.
This is from Nuno. Thank you very much.
Okay.
Let me ask you another question. This is perhaps you can also tell them there are 3 stages of EP. So this is called, well, for us in design, we say this is economic potential. It's the difference between the cost, selling price of the product minus the cost of the raw material. At your slides, you say there are 3-4 stages of EP. How do they differentiate between one to another? Is more details or how?
Yeah, we put more information to it. Let me just go back.
So it differs from one stage to another.
Yeah. So in this stage, we don't have much information. What we have is only the raw materials and the products. So if we then the products sales minus this raw material cost, we have like EP 0, economic potential 0, and then once we know some sense of the capex, and we put this capex into the equations. Right, so sales minus raw materials and then minus the capex, we get EP1. This is my own definitions. Yeah, I mean, you can always argue, but at least this is then how we proceed. Because the more we proceed to the right, the more details or information that we have. The more information that we have, more detailed calculation can be done. And then in this case, we can include as well, because we do the mass and energy balance. So we could include also the utilities in that in this calculation. So we in this EP2 we have sales minus raw materials minus capex, and as well as minus the utilities, or minus operating expenditures.
Okay, that's good.
So then that means the profit that we get from here will be lower here and then lower over there. So we can see a trend of profit reductions as we go along, which is normally the case.
Good. Thank you very much. In view of time, I think we need to close for the webinar today. For those who are IChemE member, you may sign in to the portal to get access to the recorded webinar in a couple of days. And then for those of you who would like to offer yourself as a speaker in the future webinar, please feel free to get in touch with any of our IChemE committee member. You can also log into our to IChemE website to look for our names and contacts over there. We welcome the speakers to share with us the practice in industry, which is also relevant to academic study, or any good practices in education. We always welcome speakers to share with the rest of us. So I guess that's all for today. Thank you very much, Zulfan, for your nice talk.
Thank you very much, Dominic and the others.
So thanks very much. Thanks for attending. We'll see you in the future. Thanks. Bye-bye.
Thank you. Bye-bye. Bye-bye.